Good day to everyone who will be watching. My name is Wong Summer Adeline. I am studying in Xiamen University, Malaysia, with the student ID DSC2409099. And today, I will be discussing the applications of calculus and how it can be used in real life. So today, in this presentation, I will be discussing how derivatives in calculus can be used in economics, such as functions in economics such as cost functions, revenue functions, and profit functions, average cost. Let's start with functions in economics. Now, first, we have cost function, which is a function that represents the total cost incurred by a business in producing a certain number of goods. As in all businesses, these costs can be broken down into two main components, which are fixed costs and variable costs. Let's take this equation as an example. Here, the fixed cost can be seen as the value that doesn't take x into account, such as 100 here. 100 can be anything fixed that does not depend on production, such as rent or worker salaries. And then up next, we have 20x, which is a linear cost. This represents the cost of producing one cupcake, 20 units of money. And then we have 5x squared, which represents growing inefficiencies. This represents steeper increases in costs. For example, for smaller batches, our regular employees can handle the workload efficiently. However, as production grows, the employees may need to work overtime, which is more expensive, since overtime wages grow faster than the regular wages and leads to a steeper rise in costs. And then up next, we have marginal cost, or C derivative X. So marginal cost is the derivative of cost function, and it represents the cost of producing one additional unit. This can be used to decide whether producing more units is cost effective or not. For example, from the previous cost function, the derivative of that cost function, the marginal cost function, will be 10x plus 20. Now, let's take this as an example. Let's say a company incurs fixed costs of $500, such as in rent and other things, and variable costs of 4x squared plus 220x. Write down the total cost function Cx and calculate the total cost for producing 50 units. Now, to write the total cost function Cx, you just need to combine the variable cost and the fixed cost, which will be like this. Cx equals 4x squared plus 20x plus 500. Now, to calculate the total cost of producing 50 units, 50 just needs to be substituted into the original function, which will give us the total cost of $11,500. Now, how much will producing the next unit cost the company? So if you guys can recall, producing the next unit is the function of marginal cost, which is the derivative of Cx. So first we need to derive Cx, which will give us 8x plus 20. To calculate how much producing the next unit will cost the company, we will just need to substitute 50 into the equation of 8x plus 20, which will give us 420. Now let's discuss Cx and marginal cost. This is the graph of the previous cost function, 5x squared plus 20x plus 100. Now, do note that I am limiting the x to above 0 because there's no way that realistically producing negative amounts of units is possible. Now, as you can see here, even when producing no units at all, the total cost still sits at 100. This reflects the fixed costs that have been previously mentioned. Now, let's take a look at the marginal cost C derivative x. The function of the marginal cost is 10x plus 20, and as you can see here, the function is linear and it keeps increasing. This means that the marginal cost increases as more units are produced. For example, at x equals to 0, marginal cost is equal to 20. And at x equals to 5, marginal cost is equal to 70. This shows that the more units are produced, the more expensive the next units are to be produced. The increasing graph of marginal cost reflects the quadratic term 5x squared in the original function, which models inefficiencies at higher production levels. Now, if the price of selling an additional unit or marginal revenue is higher than the marginal cost, producing that unit can be deemed profitable. Otherwise, it is not. Now, this is how businesses can use marginal cost analysis to identify when scaling production becomes too expensive. Up next, let's take a look at average cost function. So average cost function is a function that represents the cost of producing each unit of output. This provides a broader view of overall costs. Now, average cost function can be found intuitively by using the total cost function divided by the amount of units produced, or Cx divided by x. The derivative of an average cost function is called marginal average cost function. This shows how average cost changes when producing one additional unit of product. It also shows the rate of which the average cost per unit change as production rises. Now let's take a look at the difference between marginal cost and marginal average cost. So marginal cost measures the additional cost of producing one more unit, while marginal average cost measures how producing more units affect the average cost per unit. So essentially, if marginal average cost stabilizes, the business have achieved predictable average costs at higher production levels. And if it's negative, it means that the average costs are decreasing with more production. Let's take a look at this picture to understand more about it. Now, if we can see here, the total cost function and the marginal cost function is the same as before. However, if we can see, the average cost function decreases as production rises, and this is due to the fixed cost being distributed more equally amongst the products. As the average cost decreases, we can see that MAC is in negative territories, meaning that it is true that when marginal average cost is negative, the average cost is decreasing. And as ACX increases, MAC gets closer to the positive values, meaning that producing more and more units makes the average cost of each unit more expensive. Now let's take a look at the next example to understand how MAC works. Let's say a company's marginal average cost is higher than 0. What does this imply about scalability and efficiency? So first of all, it shows that there's a decreasing cost efficiency with more and more products produced. Producing additional units results in a higher average cost per unit. This might occur due to inefficiencies such as increasing variable costs or the business operating beyond its optimal production scale. This means that there's a diminishing return with every unit produced. The increase in average cost may reflect diminishing returns to scale, where additional production requires disproportionately more input, like more labor and more raw materials or higher expenses. So, what can a business do next? When MAC is higher than 0, this might mean that a business may be operating beyond its optimal production scale. Reducing and reoptimizing the production scale to a more efficient level can help restore cost efficiency. Now let's take a look at the next function, functions in economics. So a revenue function is the total income a business earns from selling X amount of goods. This function can be found by multiplying the price function by X. For example, let's say the total amount of revenue gotten from selling X items is represented by 50X minus 2X squared. Here, it implies that the price of selling an X amount of units in one order is 50 minus 2X, meaning it is a demand-driven price. So with more products purchased, the price gets lower and lower. The derivative of a revenue function is called a marginal revenue function. This function shows how revenue changes with one extra unit sold. For example, an additional 50 minus 4x of units of revenue can be earned from selling one extra unit of goods, which is the derivative of the previous revenue function. Now we can use derivatives to find the maximum amount of revenue that we can get. Let's take a look at the revenue graph from the previous slide, 50x minus 2x squared. Now, as we can see from the graph, the revenue increases at first before decreasing at marginal revenue equals to 0 because of the price reduction at higher quantity orders as mentioned before. So the solution is, in order to maximize revenue, we need to find the X amount of items at marginal revenue equals to 0 and limit order quantity to that value to prevent a drop in revenue. Let's try to solve it. Marginal revenue is equal to 50 minus 4x, as mentioned before, and we set it to 0 in order to find how much X is needed to find that maximum revenue. Now, if we solve it, we can see that X is equal to 12.5. Now, if we substitute this X back into the original revenue function, we can see how much revenue we can get maximum, which is $312.5. Now, let's take a look at the third example to understand more about revenue functions. Let's say a company sells a product where the price function is Px equals 100 minus 2x. What is the quantity of goods sold that maximizes revenue? So first of all, what we need to find is the revenue function, which is price times x. As we can see here, Px is equal to 100 minus 2x. So the revenue function is equal to 100x minus 2x squared. Now we can derive the revenue function to find 100 minus 4x. And as stated in the previous example, set it to 0 in order to find the x amount of quantity of goods sold that maximizes revenue. So here, x equals to 25 when marginal revenue is equal to 0. If the marginal cost of production as x equals 25 is known, we can compare it again to the marginal revenue to decide whether producing 25 units also maximizes profit, as is mentioned before. Now let's take a look at average revenue function. So similar to average cost function, average revenue function represents the revenue earned per unit of product sold. This can be found by dividing the total revenue by the quantity of units sold, as you can see there. Average revenue function is equal to revenue function divided by x. However, Since revenue function is equal to price times x, we can say that average revenue function is equal to the function of the price. So marginal average revenue is the derivative of the average revenue function. This function measures the rate of change of average revenue with respect to quantity. Now, when marginal average revenue is higher than 0, this means that the average revenue function is increasing, suggesting a market where price increases as quantity sold increases. Now, in a perfectly competitive market, the price stays constant, meaning the marginal average revenue is always going to be equal to 0. Now let's take a look at profit functions. So profit function is a function that describes the total profit earned by a business at production level X. This means that the total amount of units produced and the total amount of units sold is the same. So we can find profit by decreasing revenue function by the cost function. And next, marginal profit, or MP, is a function that measures the change in profit from producing and selling one more unit. As with all the previous marginal functions, the profit is increasing if the marginal profit is higher than 0, and it's decreasing if it's lower than 0. It stays stable if the marginal profit is equal to 0. Now let's take a look at the fourth example. Let's say a firm has a price demand function of Px equals 100 minus 2x and a cost function of Cx equals 20x plus 100. At what amount of units does the firm maximize profits? Now first, we need to find the revenue function, which can be found by multiplying the price function by x. So the revenue function is equal to 100x minus 2x squared. Now, since we know that profit function is equal to revenue function minus cost function, we can see that the profit function here is 80x minus 2x squared minus 100. Now, the way to find the maximum profits is the same as the way to find maximum revenue. First, we need to find the derivative of Px, or the marginal profit, and then we set it to 0 in order to find the peaking point of the profits before it starts to decrease. So the derivative of profit, Px, is equal to negative 4x plus 80. And since x maximized when marginal profit is equal to 0, we set that to 0, and then we solve for x, which is 20. So the firm maximizes profits when selling and producing 20 units. Now up next, we have average profit function, which is the function that describes the profit earned per unit of goods sold. Intuitively, the way to find this is the same as the way to find average cost, which is dividing the total profit by the total amount of units sold. This function can help businesses understand profit margins on a per unit basis and adjusts pricing or costs according to their needs. Marginal average profit is the derivative of an average profit function, and this function measures the rate of change in average profit. This function can help tell business owners how efficiently profit is changing on a per unit basis, which is essential in adjusting prices and costs. Now that we have finished discussing how calculus can be applied in economics, let's discuss Washer method next. So the Washer method is a technique used to find the volume of a solid of revolution along the x-axis. Now this can be used when the solid has a hollow donut-like shape due to the axis of revolution. So essentially, the shape has a hole that passes right through it. So these are examples of figures whose volume can be found using the Washer method. In the left picture, y equals 1, and the left picture, the x-axis, the cross-sections of these figures are going to be a circle. But since it's hollow and has empty space in the middle, if we cut it in half, we can see that it makes a donut-like shape. And the area of that donut-like shape can be found by decreasing the area of the big circle by the area of the small circle. Now, the Washer method involves integrating the function. So essentially, we calculate the total amount of the area when we divide the figure into infinite amounts of cross-sectional areas. So essentially, the thickness of the area is basically negligible, and we only count the total amount of area of the actual cross-section. When written down, the formula of the Washer method goes as follows. Volume equals pi times the integration of a from b, where a and b is the place where the figure started and ended on the axis of revolution, of the outer radius squared minus the inner radius squared. Here's a step-by-step process on how the Washer method can be used. So first of all, the first thing to do is to sketch the region. This can help us identify the area and the axis, which will help us find the limits of integration, and the inner and outer radius, which will be used in number 2 to determine the outer and inner radius. And then we use the endpoints of the region along the axis of the revolution as the limits of integration. Let's take this question as an example. Find the volume of a solid obtained by revolving the region between y equals x squared plus 2, y equals to 2, and x equals to 4 along the x-axis. Now intuitively, we can know that x equals to 4 is going to be one of the endpoints of the integration, or B. Let's first sketch the region so we can know what we are dealing with. As you can see in the picture, the shape that has been produced by the revolution is hollow and has a hole in the middle. This means that we can use the washer method in order to find the volume of the figure. Now we can determine the outer radius to be x squared plus 2 and the inner radius to be 2, and the limit of the integration to be from 0 to 4 as mentioned before. Now we just have to plug these values into the formula of the washer method to find this. So the volume of this figure is 4,352 over 15 pi units cubed. Now let's discuss our final topic, which is moments and center of mass. So center of mass in simpler terms is the balance point of an object. So let's say that you want to find the point where you can hold this thing where it balances perfectly. Now, in order to find this, we can use moments, which is used in calculus, to calculate the center of mass of an object. And this is done by integrating over its mass distribution. So let's take a look at this figure as an example. So this figure is balanced when the mass times the distance of the first object on the left is equal to the mass times the distance of the second object on the right. So if we simplify the formula, we can see that this figure is balanced at the point at the first mass times the position of the first mass plus the second mass times the position of the second mass divided by the total mass. So the top part of this formula, or the numerator, is called the moment of x. Now this can also be used with masses that are placed vertically. So the center of mass on the y-axis is the moment among the y-axis divided by the total mass. Now it is important to note that in these planes, the density will be uniform. The formula of density is mass over area. So essentially, mass is equal to density times the area. Now, since we can find the area of a region bounded by a curve by integrating that curve, we can say that mass is equal to the density of the plane times the area of the plane, or the integration from A to B for fx against dx. Now, the formula for the moment across the x-axis goes as follows. Density times the integration from A to B for fx squared over 2 dx. And for the moment along the y-axis, it's density times the integration from A to B, x times fx dx. Now let's take a look at an example so that we can see these formulas in action. Let's say that we have to find the centroid, or the center of mass, of a region bounded by y equals 2x squared in the interval 0 to 4. Now first, let's sketch the region so we can know what we're working with. So this is the curve in the interval from 0 to 4. So what we have to do, if we have to find the center of mass of the area under that curve, assuming that the density is uniform across the region. So we can do this by first finding the mass by using the formula from the previous slide. Mass equals to density times the range of the interval 0 to 4, the function of fx dx. So if we solve the equation, we can see that the mass is equal to density times 128 over 3. Now let's find the moment across the x-axis. Moment across the x-axis is equal to density times the integration from 0 to 4 of fx squared over 2 dx. Now fx squared is equal to 4x to the power of 4. So if we solve this equation, we can see that the moment across the x-axis is 2048 over 5 times the density of the plane. Now we can do the same thing for the moment along the y-axis, and we can see that along the y-axis, the moment is 128 times the density of the plane. Now we can plug in the formula from the previous slide to find the center of mass of the actual plane. So the x bar is equal to the moment along the y-axis divided by the total mass. So it's equal to 128 density divided by 128 density over 3. So we can see that the density doesn't actually play a part in the center of mass, as it's fully cancelled in the equation. So now we can see that the x bar is equal to 3. We can do the same thing with the y bar. And if we calculate the function, we can see that the y bar is equal to 9.6. So the centroid of the region, bounded by y equals 2x squared in the interval from 0 to 4, is x-axis 3 and y-axis 9.6. That is all for my presentation today. I hope that it has been a very educational presentation, and I wish you all a very nice day. Thank you.